Good afternoon, everyone, and thank you for attending today's Engage session. My name is Erin Roberts, and I'm a Public Engagement Officer at the Office of Communications here at Goddard. I'll be introducing today's topic and the panel members. The Engage series started as a way to engage with Goddard employees with Goddard's missions, programs, projects, and other topics. These sessions typically coincide with launches, milestones, or other special topics each month. Today's session is all about the XRISM mission. XRISM's acronym stands for X-ray Imaging and Spectroscopy Mission. XRISM is an upcoming observatory designed to investigate big cosmic questions, like the origins of the universe's largest structures, the fate of matter under extreme gravitational forces, and high-energy particle jet works. The mission is a collaboration between JAXA and NASA with participation from ESA. The XRISM mission is intended to restore the soft X-ray spectroscopic science capabilities lost after a series of prior JAXA missions with NASA contributions. NASA will provide the XRISM science data processing pipeline and archive, and ground station support during operations. The agency also held a mission system engineer advisory role. Let's learn more about the XRISM mission from today's panel members. First, we have Brian Williams, the XRISM project scientist. We have Rob Petrie from Goddard's Astrophysics Division Director. We have Lillian Reichenthal, the XRISM project manager. And Mihoko Yukura, XRISM's user support scientist. Thank you for being here today, and now I turn it over to Jeanette Kurzemack, who is the science writer at Goddard and our moderator for today. Thank you.
Thanks, Erin, and thanks everybody for being here today. So my first question is, what is the XRISM mission? And maybe as we sort of answer this question, we can go down the line and everybody explain their roles a little bit. So Brian, I'm going to start with you.
Sure, thanks. So as Erin said, I'm the NASA project scientist for XRISM, which is the X-ray Imaging and Spectroscopy Mission. It's a new astrophysics mission that will be launching very soon. It's a collaboration with JAXA. And the name of the game with XRISM is high resolution X-ray spectroscopy. So not only will we be able to take images of things, but we'll be able to break the light up that comes in into spectra. We can see the fingerprints of the universe and see what elements are out there creating the emission that we see. We've been able to do spectroscopy in the X-ray before, but never at such high resolution. This will really dial the resolution up by a factor of 50 or so from what we've done before. So it'll really be a game changer. It really is a new window on the universe that we have not had the capabilities of before.
Can you tell me a little bit more about what does a project scientist on a mission like this do?
So mainly my role is to ensure that these science objectives are met. We have a full 120 or so person science team that's international. We have about half are in Japan and the rest are in the US and Europe. I interface with them. I interface with the project management, with the PI. So yeah, my role is really to do a lot of things, but to make sure that overall the science of the mission is achieved.
Thanks. Rob, how about you?
So I'd like to say a few words about what Goddard's specific contribution to XRISM is. Goddard is providing two of the key components of XRISM, the X-ray telescopes and the X-ray microcalorimeter detector that allows us to do this high-resolution imaging spectroscopy. Both of these devices are the outcome of 30 to 40 years of research here at Goddard. These are devices that are made nowhere else but at Goddard. They're actually made within the X-ray Astrophysics Lab, code 662. The X-ray mirrors are, we started developing those mirrors in the 1970s. In fact, I came here in 1982 to work on these X-ray mirrors. And the idea of these mirrors is to maximize the amount of X-ray light that one receives at a minimum of weight. And of course, when you're launching things into space, the premium is on mass. And prior X-ray mirrors were very massive because they had very good figure and they were designed to do very high quality imaging. For the type of mirror we developed here, we sacrificed a little bit of the angular resolution in order to achieve much more light gathering power, which is really what you need for things like spectroscopy. The first mirror of this sort flew in space on the Broadband X-ray telescope back in 1990. And then since then, we've been involved with the Japanese on a series of X-ray missions, some of which we will talk about later. But we've flown about 20 of these missions, 20 of these mirrors in space so far. The X-ray calorimeter was also developed here in about 1983. It was developed by Harvey Moseley with some help from Richard Michotsky. These are two of our most distinguished emeritus scientists. The idea there was to figure out how to do a combination of imaging and high-resolution spectroscopy, a combination of which is actually very difficult for basically any wavelength region. The idea, the way that the X-ray calorimeter works is that every X-ray photon that impinges on the detector is turned into a heat pulse. And then you actually measure the temperature rise in a detector due to the X-ray impinging on the detector. We developed these originally for what was known as the AXAF mission, which then became the Chandra X-ray Observatory. Along the way, we got thrown off because we were too expensive. But we found a home on Astro-E, which was a Japanese, a JAXA mission. Astro-E was launched in 2000 and had the unfortunate end of falling into the ocean because the first stage failed. We followed that up with a recovery mission called Astro-E 2. And we had a systems engineering error which caused the calorimeter to not work. Doing these calorimeters is hard. And then we followed that up in 2016 with Hitomi, which had a slightly more advanced version of the calorimeter. Calorimeter worked beautifully, but after 37 days of being on orbit, there was an error in a command that caused the spacecraft to spin up and break up. So this is our fourth time through with the Japanese on a mission. The calorimeter is going to produce revolutionary science, and we've made every effort to make sure that we don't have similar unfortunate endings we've had with previous missions.
Thanks, Rob. Lil, how about you?
So as you mentioned before, I'm the project manager for XRISM, so I'm responsible for in-house build of the calorimeter, the X-ray mirrors, and also the work that's done at the Science Data Center that we're doing, and also the ground station that we're supporting. But I also work directly with the Japanese for overall for the project. And as mentioned before, we had a little bit of an advisory role in this mission with mission systems engineering, which is very unusual. It is not typical between agency to agency, but was agreed to after the aftermath of Hitomi or Astro-H. And that too has worked out pretty well for us. So, both roles of working between NASA and JAXA at the same level as they are, and then over here in the US with the management of the hardware at Goddard.
How about you, Mihoko?
So I'm XRISM user support scientist and responsible for assisting in making the best use of the XRISM by creating and maintaining the documents, answering the individual questions from the astronomical communities, and then help organize the guest observer proposal peer review. So XRISM is the NASA and JAXA collaborative mission, and both NASA and then JAXA are taking on the lead on developing instrument, satellite, and software, data processing software, as well as formulating the scientific observing plan. But in addition to the NASA and then JAXA, there are many research institutes from US, Japan, and then Europe contributing the XRISM mission. And the XRISM data were initially available to the XRISM science team, but eventually all the data and then observing time will be accessible to the researchers all over the world, this including US scientists, graduate student, undergraduate student, and anybody who are interested in looking into the universe by high-resolution X-ray spectroscopy.
Awesome. Thanks, all. So we kind of touched on this a little bit, but maybe we could go a little bit more into how XRISM is going to do its science. And I'm going to throw this one to you, Brian.
Sure. So as Rob said earlier, it's an interesting way that we do spectroscopy. We don't necessarily pass light through a prism. I mean, people think spectroscopy and, the Pink Floyd album cover comes to mind of a prism and then you have a rainbow of light. That is one way to do spectroscopy. That's absolutely not the way we do it here. Every photon that comes in, we record. So we're not like optical astronomy where you just have trillions of photons at any given time. Our count rates are fairly low. The typical X-ray source in the sky one photon per second might come in. So we can tag those as they come in, and we can record not only the image or the location of where they came from, but the amount of energy they have by how much heat they impart into the detector. So we have to get our detector very cold. In fact, we have to take, the detector is about the size of your pinky nail or so, and all the supporting structure as part of the cryogenics around it, that entire structure is meant to keep it cold. So it actually cools it down to 50 millikelvin, which is 50 thousandths of a degree above absolute zero. So people think of space as being cold, but for us, space is too hot. We have to take refrigeration systems into space just to cool the detector down to such a low temperature that an individual photon will heat it up. And we measure that heat change, we backtrack out what the energy is, and we collect a few 100,000 photons, we construct a spectrum out of that.
That's pretty cool. So when you're doing spectroscopy, what kinds of things are you learning about the objects that you're looking at with a microcalorimeter spectrometer?
So I don't know what famous astronomer once said this, but I've heard it said before that if a picture is worth 1,000 words, then a spectrum is worth 1,000 pictures. So when you take an image of something, you're learning about the spatial distribution of it, but you really need the spectra to figure out what it's made of. What are the elements in that cloud of gas or in that surrounding that black hole as it's falling in. So that's how we really take, it really puts the physics in astrophysics when you can do spectroscopy.
I'm going to borrow that line. That's a good one. Physics and astrophysics. Rob, maybe you could kind of talk a little bit about the X-ray mirrors that are on XRISM and why X-ray mirrors look so different from the other kinds of astrophysical mirrors that people may know about.
Sure, I can talk about that briefly. So, as most of you know, you visualize in your head what an ordinary telescope looks like, and we'll take our favorite telescope, JWST, as an example. For any ordinary telescope that's reflecting visible light, or in the case of James Webb, infrared, what you normally see is that the light comes in and then bounces off the surface at essentially normal incidence. Well, if you try to do that with X-rays, the X-ray just penetrates into the material. It does not reflect. That's why X-rays are called penetrating radiation. But we can use the trick of physics, kind of like skipping a stone off of a lake, where if you hold a reflecting surface at a very shallow angle compared to the way the light is coming in and bounce the light off at a very shallow grazing angle, you can actually get the X-rays to reflect almost with 100% efficiency. So if you take two of those surfaces and you put them one after another in a particular geometry, you can actually replicate what's effectively a simple convex lens. And in fact, when we do X-ray optics, if you use that analogy, you could actually use the lens formula to figure out your focal length and how your optics will perform. So by doing these two reflections, we bounce things. But if you think about it, if you make a surface like that, it doesn't use up a lot of the space there, a lot of the aperture. So we do a second trick, which is we sequentially nest a whole series of these mirrors to fill up the aperture so that we maximize the light gathering power of the X-ray telescope. And this is a fairly conventional thing that we do. For the case of XRISM, we actually nest something like 200 surfaces in order to fill up that aperture. And that gives us sufficient light gathering power so that we can see a lot of the very low flux X-ray objects that Brian referred to.
Awesome. So my next question is what is the most exciting science that you think XRISM will do? And I think, Nihoko, I'm going to start with you.
Okay, so XRISM is a general purpose X-ray observatory and will observe various variety of the astrophysical objects such as stars, black holes, supernova remnant galaxies and cluster of galaxies. And then I will start with a couple of examples of exciting science that we expect XRISM would have. And one of the science objectives is to study evolution of the universe by observing galaxy clusters. Clusters of the galaxies are the biggest building blocks in the universe, and much of the normal matter is in the form of the hot X-ray emitting gas, filling in between individual galaxies, known as intercluster medium, and shocks by galaxy mergers and accreting matters, and also the feedback from active galactic nucleus will heat the gas to the very high temperature with with the resolved instrument. XRISM will detect emission lines from the emitted by the hot gas, and making detailed measurement of the temperatures, chemical maps, abundance maps, and then motion of the gas. So we can try to answer questions such as what is the cosmic history of the intercluster medium, how does it's assembled into such a large-scale structures, what is the chemical composition of the hot gas, and how do the clusters enriched by stars and supernova across the cosmic time. So understanding how the universe gets enriched is another exciting science from the XRISM. But in addition to the XRISM, cluster galaxies, many other astrophysical objects will study the chemical enrichment of the universe. One of the examples is the starburst galaxies, which is my favorite object. Starburst galaxy often has this galactic wind driven by intense star-forming activity, and XRISM will tell us how far the metal will be transported out of the galaxies. Also, the XRISM will measure the velocity of the hot wind for the first time to constrain the total energy of the hot wind, and answering questions like how do the wind blow through the galaxies, how far do wind travel, and then what is the fate of the wind. So now I think Rob will introduce other interesting, exciting science about XRISM.
Right. So at the center of pretty much every galaxy is a black hole, a massive black hole, something from either a million times the mass of the sun to up to billions of times the mass of the sun. And the size of the black hole, strangely enough, correlates with the size of the galaxy. And what goes on in the very center of the galaxy in that black hole actually affects the galactic dynamics in ways that we don't understand. With XRISM, we will study the black holes. Black holes were discovered using X-rays. So black holes that's basically pretty much garden variety X-ray astronomy. But what XRISM can do is it can study the region around the black hole. The X-rays are created by gas around the black hole that's getting accelerated by the intense gravitational field. There's also another acceleration process that goes on that when there's, as Mihoko just mentioned, winds that get blown out of the black hole as a result of the interaction between the matter flowing in and the black hole itself. Those winds and the inflows both influence the size and the dynamics of the galaxies. What XRISM will be able to do with its precise spectroscopy is measure the velocities of the inflow, the velocities of the outflow, the composition, what matter, what elements are making up the inflow, and really give us a much better handle on what goes on near the black hole so that we can relate better to what's going on in the galaxy as a whole. I think that's one of the most exciting contributions that XRISM will make over the next several years.
What about you, Brian? What do you think is going to be the most exciting science XRISM will do?
Well, those were great answers. I can't add too much more to that, but I would emphasize what Mihoko said, that we are a general purpose astrophysical observatory. There's not one science question or one science target that we're looking at. Pretty much if it's in the universe and it emits an X-rays, we can look at it. It's important that we do X-ray astronomy because there are things that we look at. For instance, the hot gas that's in between galaxies and clusters. Some of that stuff is invisible to other telescopes. Even Hubble and Webb, if you were to point at these incredibly high temperature plasmas, you wouldn't see anything. That's why we have to go to the X-rays. So as Rob said, we'll do all sorts of science. My personal favorite type of science are from the remains of exploded stars. So supernovae go off a few times a century in a galaxy. They're incredibly powerful events. They can outshine their entire galaxy for several weeks. The remains of those, though, are visible for thousands of years. And one of the easiest ways to see those, because it's now a very hot cloud of expanding gas, is in the X-rays. So we will learn a lot on objects like this that are spatially extended, but we'll be able to get spectroscopy from. So we'll learn not only what do they look like from a spatial sense, but also what the elements are that are created in that star or synthesized in the post-shock environment.
Cool. Well, I'm going to ask you a question, and I was wondering if you could talk a little bit about how XRISM leverages previous X-ray calorimeter missions. Rob talked a little bit about this, but maybe you could go into a little bit more detail.
We absolutely leverage previous missions, but in different ways. Astro-H did a lot to bring around the engineering that was needed for the calorimeter, spectrometer, and even for our cooling system, our ADRs on there. That was really important. As any complex instrument is, it's really hard to design and build it and have it done the first time. So we definitely were able to leverage that experience from that. In addition to that, because of that recently turning around and deciding to do another mission, I think Goddard and headquarters did a really great job in looking into the lessons learned and looking into it from a technical and a programmatic perspective, and what worked, what didn't work, and that's NASA and JAXA. I didn't mean to exclude JAXA. What worked, what didn't work from all of those perspectives, and then we incorporated into how we decided to do our work going forward. Programmatically with our organizational structure, which really, if that didn't happen, helped enable communication and everything else. That was the key that leveraged other things that we could be able to do. This was a rebuild, so of course we leveraged the design of the actual hardware for the mirrors also. And so having the team, many of the team members were able to come back again, and that was very helpful also. So there was leveraging in every aspect, and down to even risk management. All the risks and issues and concerns and worries that were not able to be resolved on Astro-H were brought up front and center for us to address early on in the mission, and really proud to say that we beat down every single one of those by the time we finished, which meant communicating to our colleagues what the issues were, even though we had built it before, prioritizing what was really a concern, and then coming up together a solution that really benefit, I think, for this whole mission.
Rob, you kind of touched on this, I think, when you were talking about sort of, looking at hot gas with missions like Hubble and Webb. They don't see that. But could you talk a little bit more about like how XRISM will complement sort of the entire suite of astrophysics missions that are operating right now?
Okay, so there's many missions operating, and of course, the first thing is that we are an X-ray mission, which means, as Brian said, we see things in the X-ray that are not visible to Hubble or to James Webb or to many of the other observatories. And so just being able to see the phenomena from that different perspective, a different color of the spectrum, so to speak, we're being able to get a fuller picture of everything that goes on in both the nearby and the distant universe. Specifically, though, with XRISM, we have this high-resolution spectral capability, which is going to complement not only the broader range of observatories, but actually X-ray observatories. This is a unique capability, and never before have we been able to simultaneously take a picture and take effectively a color picture and understand within objects like the supernova remnants that Brian talked about and the clusters of galaxies Mahoko mentioned, the ability to understand where the iron is, where the oxygen is, how the gas mixes up, what the velocities of the gases around the central object that's powering the system. All of that stuff all that information is unique and uniquely available in the X-ray. And then we put that with a picture, say, of the radio emission, where the radio emission is seeing the high energy electrons being ejected in jets. We can understand then the relationship between those jets and the infalling matter. And we can look at in the visible, there's hydrogen filaments around these objects, and we can see where the 1,000-degree gas is and 100-degree gas from Webb. And then we look at the million-degree gas from the X-ray. We can understand then the interrelationships. It really gives us a much deeper view into the astrophysics of any of these systems.
Very neat. Well, could you talk a little bit more about sort of the collaboration between NASA and JAXA on XRISM and sort of how that came together and what it looked like?
Yeah, from that perspective, because we have many NASA-JAXA collaborations here at Goddard and with NASA, but what was really unique for this, because it was a design from in a sense from the 1990s and a collaboration with the Japanese early on, we actually literally built it together. We actually bring over components. It's not like what we typically have here where we deliver a box and we have very clean electrical, mechanical interfaces. We actually literally build it together with the Japanese in Japan, which is kind of hard to do a half a world away and something we typically wouldn't try to do nowadays. It's just very complicated when you're logistically so far apart. So from that perspective, it meant that we really needed to up our game with respect to how we collaborated. And some of the things with from our lessons learned and our new organizational structure, it allowed us to enable what we called like a joint systems engineering team that consisted of JAXA and NASA leads for systems engineering for the instrument and for the spacecraft. So that way we can we can work together to find solutions at a lower level. It didn't exist before, and if they did have that exist to a certain extent, but didn't work on Astro-H because the organizational structure wasn't in place. So in this sense, we really were able to. We're in a world with Teams now and Zoom. And I can tell you right now, even today, because we have testing going on right now, we've got Zoom, we've got cameras, we've got everything going on, and I don't even know how we'd got through the pandemic if we didn't have all that. We literally were in the lab with them when we couldn't be in the lab, working through our night, Japanese day, to get the work done. So it's a very, very close relationship at the instrument level, and then at the spacecraft level, having this additional advisory role for systems engineering. That was unique, but that was a way for us to be able to work with our colleagues to identify things that were risk to mission success. That was our primary goal here. We respect our agencies and the work that they actually do, but we were just making sure that there were any risks to mission success and that we had a very good collaboration at that level too.
Let's see. Brian, maybe this is a question for you. We've talked a lot about spectroscopy, but there is another instrument on XRISM. So can you talk a little bit about what Extend will do and how it will contribute?
Yeah, so most of what we've talked about has been using the Resolve instrument Resolve is not an acronym, it's just a word we came up with because it resolves the spectral lines. The other instrument, though, on XRISM is called Extend. It is a wide field of view imager. It's almost 40 arc minutes on a side, which is, to give you perspective, it would easily fit the full moon inside if you were to point it at the moon and get some stuff outside of that as well. That's very large for astronomical telescopes, especially space-based instruments. Now, you can't have it all with instruments, so you have to sacrifice something. So if we have this massive field of view and a fair bit of collecting area, we did sacrifice some of the angular resolution to make these lightweight mirrors that are easier to produce than some of the previous high-resolution mirrors have been. So Extend has about arc minute or so angular resolution, so it won't quite have the imaging capabilities of some previous X-ray telescopes or optical or infrared, but it will have this massive field of view. And Resolve and Extend operate simultaneously, and the Resolve field of view is contained within the Extend field of view. So whatever you're observing with Resolve, you'll see the entire surroundings around that, and we'll be able to map out large regions very quickly using something like several degrees across if we need to with Extend.
In comparison to sort of like the spatial resolution that like Chandra has, could you explain like Chandra produces some very beautiful images. What will XRISM's images look like in comparison?
They won't look that nice. Chandra has arc second level resolution. We have about arc minute resolution, so that's a factor of 60. So yeah, about 60, probably closer to 100 times less resolution. But again, we have the wide field of view. Extend also does have spectroscopic capabilities as well. It won't produce the high resolution spectra that Resolve will, but it will produce a similar quality spectra to what Chandra can produce.
And what is the benefit of looking at sort of the spectroscopy data in collaboration with an X-ray image like that? What things can you tease out of the data when you have both of those things?
Well, you're really getting the three-dimensional picture of what's going on. The image gives you the 2D, it's like looking at a painting. You get the X direction and the Y direction. The spectroscopy really gives us the Z direction of what's happening. Not only what are the velocities maybe of the gas as it's moving, but what's the composition. Mm-hmm. We always, there's a lot of analogies here. It's sort of like scanning a barcode. It's, every element in the universe gives off a unique signature. And we can tease that out of the data from both of these instruments.
Let's see, Mihoko, maybe you could had when you introduced yourself talked about sort of the XRISM sort of guest observer facility. Could you talk a little bit about how scientists around the world are going to be able to access XRISM's data?
So after the launch, there will be a 4 months of a commissioning period, and after that, 6 months of the performance verification period. And during those period, XRISM will observe the target that XRISM science team already selected. But after the the performance verification period, so about 10 months after the launch, the XRISM will be open to the public. So if everything goes well, there will be a call for proposal in this fall. So anybody who have a cool idea for using XRISM can submit proposal and obtain the data if the peer review selects the proposal. If people do not want to go through proposing the target process, they can still obtain the data after the target exclusive use periods are over. All the data, including the performance verification targets, will be public through NASA's HISAC archive, and HISAC also provide data analysis software. So anybody who is interested in the XRISM science will have access to the XRISM data.
Very exciting.
And I just wanted to add to that too, that for, after this, initial 4 months of checkout and then 6 months of performance verification, the rest of the duration of this mission, which we hope is many years, is purely a guest observer facility. So it's just open to the entire world to write proposals in. So we'll do this on an annual basis as we do with other NASA missions. So
very cool. Lil, could you tell us a little bit about sort of XRISM's getting ready for launch? Could you talk about sort of where is it going to launch and when, and what are the plans for that?
So excuse me, the launch is going to be on August 26th in Japan, August 25th here in the US. It's at 9:34 in the morning in Japan. It's going to be the evening here. We're going to have a launch event here at Goddard, by the way, from 7 to 9 p.m. in the evening on Friday, August 25th. It'll be at the Tanegashima Space Center in Japan. So if you think of all the main Japanese islands, it's one of the first smaller islands right off the main islands going south of there. And it's a very small island that they have, and that's where they have the Space Center. I don't know if I remember the other question. Anything for preparation. So recently, as of just today, we're beginning our final cool down for launch. The instrument's going to get cooled down to a very cold temperature for launch. And this is our last time we get to check it out while it's on the pad. Just recently, last week, the vehicle was attached to the payload attached fitting, and then it was lifted to put on top of the second stage of the rocket that has our co-manifest that's with this mission called SLIM. And SLIM is a lunar mission. It's JAXA's mission. So then it got encased with the fairing, and it on August 11th moved to the vehicle assembly building there in Japan. So the weather is good now. We just last week went through 2 typhoons because it happens to be in like equivalent area of Florida, like Florida in Japan, and it is typhoon season. Right now it's looking pretty good. I hope I'm not jinxing it. We're a little bit more than a week away, but the weather there has been pretty good. And now that it's in the vehicle assembly building, it's the final cool down and then top off, and then all the last minute activities getting ready for launch.
Very exciting. So after launch, we've kind of talked about, that Resolve has to operate at a very cold temperature in order to do the spectroscopy that it will do. So would someone be able to talk about sort of how do we get to that fraction of a degree above absolute zero once we're in space?
So once we're in space, so we won't launch unless we have enough liquid helium and we get down to a certain temperature, and we have that temperature as we go up. So we already begin. We have the cryocoolers working, but the instrument will be off at that time. Once we get into space, and not too long after we get into space, we begin the cooling. And I really don't remember the exact period it takes to do the exact cool down, but we begin commissioning of the Resolve instruments, so it'll be cool by then, within about 3 to 4 weeks after that. And then we have about a month of commissioning activities. So we have 3 months total. Of course, the spacecraft commissioning will come first.
Yeah. Can you explain what you mean by commissioning? What does commissioning mean?
Commissioning, thank you. Commissioning is actually checkout. We all think it's kind of, at least on the engineering side, in a sense, we think it's, okay, we launch it and we're kind of done, but we really actually need to check out and make sure everything is in working order once you get up in space, and including the instrument. We understand how the instrument works on the ground through extensive testing and extensive calibration, but we need to actually do the same thing in space from an initial checkout point of view, and then through the performance verification phase also. So the 3 months is the checkout, telling us that once it's completed that we're ready for mission operations.
Excellent, thank you so much. Are we ready for our Q&A period? All right. Well, thank you all so much. I'm going to hand this back to Erin. To keep up with news about XRISM, please follow us on X and Facebook at NASA Universe. Thank you.
Thank you, panel members. Thank you, Jeanette. Okay, so feel free to walk into the aisles and ask the questions in the room, but we have some ready online already. So a lot of XRISM's testing happened during the COVID-19 pandemic. How did the team manage the problems and issues arise from that?
So
Definitely deferring
okay.
that.
So everybody here on center was impacted by the pandemic, so that's a given. So nothing here is unusual for it. What made it more challenging here was, to set it in the context, we had just delivered our hardware to Japan in the end of 2019. At the beginning of 2019, we finished integrating the hardware in Japan together with the Japanese. And in February, we were actually out in Japan right when the pandemic was starting, but we were all clueless about what it was. And at that time, we were just getting ready for our first cool down, and that's when the pandemic started. So our first cool down, very exciting time, and we knew we had about a year beforehand, we had been working with the JAXA team with, it really doesn't make sense that we constantly have to travel back and forth and be there in the lab. Is there any way we can send telemetry back here? And we had actually worked that over, a lesson learned, 2 years, working through it. Well, it actually came to be right around that time period, the beginnings of it, and that just got itself accelerated. And within a week, when we had a sense that we were going to be closing down here, we made sure my office was full of computers that we used to support things remotely between Japan and the US, and that we could actually log in remotely to capture the data, archive and process the data, was all kind of my office and in offices in Building 34. So we were very busy getting this up. Again, Teams is just starting to come up. We just learned the word Zoom and everything. And thankfully, that was all coming to be right around the same time. Well, once we went into the cold test, and we still hadn't shut down the governments yet and everybody, we found out we had a leak within the door. You only see a leak when you're in cryogenic temperature, so you have to get it cold. It was such a leak that you couldn't see at warm temperature because the leak was equivalent. The leak was the size of, if you can imagine a balloon the size of my fingernail, at warm temperatures, it would take about 1,000 years to blow up that balloon. That's how small that leak was at warm temperature. The only way to find it is in cold temperature, and finding is like looking for a needle in a haystack. And right at that time, pandemic hit, everything shut down, and that got pretty complicated. We used these remote tools, which really helped us kind of be in the lab with them as we were troubleshooting, using our experts here at Goddard. We have cryogenic experts and our science team, and all work together to try to identify where the leak is. Once we identified it was in the JAXA hardware, we recognized with a big sigh, we have to travel to Japan. At that time, we were still working on, I can't think of a better word than the bureaucracy that was needed to actually come into work, let alone to travel, send materials, do whatever we need, send the hardware, equipment, well, we need better leak detectors, everything that we needed to make this work. And if I didn't have the support services here at Goddard, I don't know where we would have been without it. To get the hardware we needed there when shipping, when everything is closed down, was very difficult, but we got the support of the center. It took a little bit of time within our center, but we also had to do the same thing with JAXA. Not only did we have to get approval through the State Department, the government of Japan, and the embassies within Japan, we had to go to the local communities and the buildings that we were in to come up with a plan, a process, quarantine plan on how this is actually going to work. And I tell you, it changed on a monthly basis and got that much more complicated during the Olympics. I can't even explain that because that really complicated things also. But I'm proud to say with all that, it was very, very challenging for the team. You had to undergo the 2 weeks of quarantine. You had to make sure that you had the testing done within a certain time period, like 36 hours before you left. And we didn't even have testing facilities up that were able to provide that quickly, or sometimes that fell apart. Well, you can't send them over. But both NASA and JAXA and all these organizations really helped make this happen. And it took everyone beyond the team, and the team especially. It was a big sacrifice for being out there in Japan.
Wow, that's incredible.
So, but it worked, and we got out there I know it's more than 50 trips. I think it ended up being like 75 trips back and forth. No one got COVID or brought it to Japan.
Wow.
Or brought it back with them from going to Japan that whole time, because we did it here, where this is the most respectful team I've ever seen, where they wore their masks, and everybody was the same there too.
Wow, that's great. And well, navigating there and back and all, how did you and your team deal with the time difference and the traveling time and kind of that all comes with going over to Japan?
Well, that's hard. This team has a lot of experience with it. I heard a big sigh over here. They have a lot of experience, as I do, with jet lag and getting over there, and you have to be so careful about it. But this team is so determined and so cannot wait for this instrument to get up there in space. They've been waiting an awful long time, that they were extremely dedicated for this. I can say that it gets a little bit harder as we all get older and being able to maintain it, but we did have a full days of work here, and then we were online with Japan and also had a team there in Japan a lot of times at night. So it was a lot of demands during that time period, and still continues to be actually until we launch.
Right. And so what happens once launch happens and it's successful? What's the next step from there?
Is the commissioning time period. Okay. So when we do the checkout and really check out and thoroughly learn the instrument, learn how it's operating in space, how that compares to how the testing in Japan, so we can understand what science we'll be producing afterwards.
Great. All right, so no questions here. So we have two more from online. Kevin H. asked, what is the expected mission lifetime?
3 years.
3 years.
However, I think...
At least 3 years.
At least 3 years. That's what's written down
That's
legally.
the official number, right?
The official number, and 3 years from launch. But we do, I believe, have enough liquid helium right now, and based upon the performance, and we've been checking for any further leaks, it is so leak tight right now. So based upon that, it looks like we have enough cryogen for 4.5 years, but we also have a cryogen-free mode. So once we do run out of cryogen, we'll be able to extend that a bit longer and still do science.
Let me make a comment about that too, to understand how good a cryogenic system we have here. The liquid helium that we've been referring to, which keeps the innards really cold, we have the equivalent of about a 10-gallon fish tank. Mm-hmm. So we have 10 gallons of helium, and that lasts 4.5 years. So you can do the math and figure out how quickly or how slowly that boils off. It's pretty astoundingly efficient.
Yeah. And as we said, once the helium is gone, the mission isn't over. We can operate just fine without that. It just takes us a little bit longer to pump down to those temperatures that we need. But, you know, I have no idea how long we'll last, but I hope that we last into the next decade.
All right, we'll take a question here in the audience.
You mentioned about looking at different objects. What's the duration or time frame that it takes for you to get, if you choose something? I mean, looking at that, I mean, that looks like just a 5x5 there. If that's the surface area that you're pulling data in, what's the time frame to get all that data you want to look at an object to then begin to start doing science on it?
You want to take that or you want
Did it?
Yeah, I can take that. So if we're looking at an object that's the size of the detector, then the data come down. They get preliminary processing on the spacecraft, get put into a telemetry stream and come down. We're doing telemetry dumps daily or more frequently than that. And then our processing pipeline is actually driven by the fact that we need ancillary data associated with the orbit before we can actually do a full-up processing. But we can do a quick look processing basically instantaneously once the data come down to the ground. And so we're not in constant contact with the spacecraft, but we're doing passes a couple of times a day. There's another aspect to this, because many of the objects we want to look at in space are far larger in extent than that array. That array is only 3 arc minutes on a side, and so it's quite small. It's actually probably the size of the wide field camera on Hubble. And so if we're looking at an object that's larger, then you need to tile, and of course that takes longer. Your typical observation, in order to get enough data to have a good quality spectrum here, is on the order of a day or two. So if we wanted to tile a region of space that's, say, a 3x3 array, it would take us a week or two to do that and actually collect the data. But once the data are taken, they come basically right down to the ground, and we can process them pretty quickly.
I'll follow on with the question, the answer actually, that it is limited by the lifetime of the helium on board. So is the imaging and spectroscopy be done using the same X-ray? Like, will it be used for doing both?
Yeah, the two instruments operate simultaneously, and they
Okay.
see the same X-rays coming in.
Right. There's two separate light paths. There's actually two identical telescopes,
Yep.
both of which were provided by us. And so, in fact, the images from the two telescopes are virtually identical. We had a very hard time determining which one we should use for which detector. So you get, in the extend detector, you get this nice 40 arc minute on a side image, and at the same time, on the resolve detector, you're getting this 3 arc minute image plus the high resolution data that come with the image.
Yeah, and those two mirrors, by the way, are a little bit smaller than this table. They would fit on this table. They're about 45 centimeters in diameter. And on the spacecraft, they're roughly about as far apart as these two tables are. So they just sit right next to each other.
And so imaging, shouldn't the imaging work after the spectroscopy? I mean, I can imagine the spectroscopy is limited by, it needs to be really cool because you need to be really sensitive to the energy. And you need the same energy resolution for imaging as well.
I didn't quite catch the whole question, sorry.
What I'm trying to say is, I understand for spectroscopy, you need it to be really, really cool because you want to find out the exact energy of that X-ray. Is that a requirement for the imaging as well?
Oh, no, it's not a requirement. So the other instrument, Extend, the wide field of view, that is not cryogenically cooled.
Right.
Thank you.
Sure.
2 questions in one. Can you remind us of how far out in space the instrument will be, and will it interface with James Webb at all?
So it's not very far. It's in low Earth orbit. I think 550 kilometers or
That's
so.
right.
So yeah, 31-degree inclination, low Earth orbit. Will we interface with James Webb? Eventually, yes. We will. The entire astrophysical suite. We like to talk to each other. The missions talk to each other. They sometimes do joint observations. In the first year of observations, we won't do anything joint with other missions. We'll just do our own thing. But yeah, as we mature and get into the second year and on, we'll certainly have joint plans with all of NASA's astrophysics missions.
Would you contrast the type of science that this mission will do with the one done by the Rossi X-ray Timing Explorer mission?
Rossi.
RX.
Okay.
RXT.
I'll take that,
Yeah.
right. So Rossi had very different scientific objectives. Rossi was a very large collecting area detector. So it was designed to detect a huge number of photons from relatively bright sources. And the idea and the principle behind Rossi was to get enough photons so you could look at the time signatures that are produced by various kinds of objects. So the orbits associated with neutron stars that orbit around ordinary stars, or black holes that orbit around stars, or the pulses that come from neutron stars. And so the emphasis of RXTE was basically timing. It did have some spectroscopy, but the precision of the spectroscopy that Rossi could do is something like 200 times less sensitive than what XRISM can do. That's the gain we get with XRISM. With XRISM, we can do that kind of timing, but we don't have to concentrate on the very bright objects. In fact, many of the bright objects that Rossi would detect are too bright for our detector. So we wouldn't necessarily get very good signal from them. We'd have to play some special games in order to actually even observe those objects. So we're focusing in on less bright objects, more distant objects, therefore. We're not focusing necessarily on time signatures. We're focusing more on the spectra, the colors that are produced, to try to diagnose, again, the atomic composition, the velocities that we see, whether the gas is blue shifted or red shifted away from a central object, how it's mixed in its environment. So there's very different scientific emphasis here between XRISM and Rossi.
So getting into the research and development, how long have you been working on CRISM, time frame wise? Like maybe in your career?
Well, it is my career. So again, the X-ray mirrors are pretty much direct descendants of work that Peter Sorlivito started in the mid-'70s here at Goddard. And these are designed to be low-cost, low-mass light buckets with modest angular resolution. They're not designed, again, to do the high-precision imaging that, say, a Chandra will do. And so, one of these telescopes costs a couple of $1 million to build. The Chandra Mirror cost $100 million to build. So, there really is a significant difference in terms of cost. And over the years, we've evolved the design. We've come up with better ways of making the mirrors. But the fundamental principle really hasn't changed for what Peter came up with in the 1970s. Peter has since retired, and so the projects have been taken over by others, in particular Takashi Okajima. But this all goes back to him. For the X-ray calorimeters, those were invented in the early 80s. And the heritage is actually from infrared bolometers. Harvey Moseley was a Goddard scientist who came here to work on, to develop infrared bolometers for things like COBE. And Harvey recognized that, gee, maybe we could make an X-ray bolometer. And went off and did some calculations, got people like John Mather involved in doing theoretical calculations, and showed in the 80s that you could really do very high resolution X-ray spectroscopy with these kinds of devices. And then we went on this very long, 10-year-long process using things like Director's Discretionary Fund to fund us, all internal work within Code 662 to figure out how to make these things work. And in the end, we've now had this series of detectors that have gotten slightly better with time. And there's a huge future here. So this a second generation X-ray calorimeter mission will be flying on Athena, which is a major European mission. So this has been a product, like I said, this is all internal to Goddard that we've done this. And it's a real testament to the people who work here and to the center as a whole who have supported us over the years that we were able to do this long-term technology development.
Well, very exciting. We're all excited for the launch that's upcoming. Do you want to give any acknowledgement or thank you to the team that might be watching online?
Yes, thank you. Yeah, I mean, as Rob said, this is a very long effort. There are people who've done their entire careers on this. There are people who are now retired. There are people who are passed away who worked on this, the technology behind these missions. So it's a very long endeavor. I mean, and if you guys want to...
a big thank you to the folks on Astro-E, Astro-E2, Astro-H, and CRISM. Even though some of them couldn't join us for CRISM, totally get it. It was a really hard job on all those other missions, and we've leveraged all that. And I hope you can appreciate that your efforts have been put into what we have here right now. In addition, not only for the team, because they really have dedicated a lot, but everyone, again, the support services here on center. We're nothing without somebody being able to put travel orders in and help us out with these last minute things, or the processing or shipping, or you just name it. That's part of what makes us work.
And one last thing here. So yeah, everybody who Lil and Brian have talked about, I want to thank. But also, we got unwavering support from NASA headquarters,
Absolutely.
from Paul Hertz in particular, and from center management.
Yeah.
So nothing like this happens without having that kind of support. So everybody pitched in on this, and we hope we can bring this home next Friday night when we launch this thing.
That's right. All right. Well, thank you so much for participating in today's Engage session. Let's give a hand to our panel members. All right. Thank you very much. Keep your eye out in Dateline for the next Engage session. Thanks for joining us.